Hello. Good afternoon. Did everybody have tons of coffee? Because I'm going to talk about functional safety. Yay. So, my name is Rebeca Delgato. I work in the autonomous driving industry, and this is a very exciting field these days, and everybody's very excited. There's tons of investment being made, a lot of innovation, very, very smart people looking at the challenge. So today I wanted to talk very specifically about the reliability, security, and functional safety challenges that the industry is facing, and some of the trends to address some of these engineering very complex questions. We're going to read all of the legal notices. Thank you. So everybody's very excited about this field. There's a lot of questions and a lot of hopes and hype. Everything from level 2 already very widely deployed, and how to evolve this into level 2 plus, level 3, and then eventually, and in a very disruptive manner as well, to level 4 levels of autonomy. And enablement technologies that are being leveraged in this regard that I'm going to talk about today are functional safety standards and efforts to create guidelines and strategies on how to address these safety implementations, architectures that address these safety and security requirements while being scalable and being able to deliver the compute compelling requirements. So how all of these things help or detract from each other, and then being able to support the requirements to enable the adoption of this technology. Oh, this big button, got it. Could you go back one, please? Thank you. So historically, the automotive industry has been working on how to deploy reliable systems for a very long time. I mean, at the end of the day, when you deploy these kind of systems in such large volumes, you can't afford to make mistakes. And particularly in the area of safety, the functional safety standard that everybody is very well aware of and very familiar with, ISO 26262, got first released in 2011. There was a revision recently released in 2018. And the goal of this standard is to address faults in a system. You want to make sure that your system has an ability to detect failures, and whether these failures are due to just hardware random failures, or whether they're latent or transient, or if your systematic approach to development in the development lifecycle addresses this. So this is to address that the functionality of your system is safe, and if there's a failure, you can detect it, and then you can do something about it, and then do a strategy that allows you to safely fail, right? But all of that is in the context of failures, when there's a problem in your system. So great, that's a very good foundation that's necessary for us to understand that your system is capable of identifying if something's going wrong. This is a good baseline, and I'm going to talk about how maybe this safety standard is not sufficient as the autonomous driving system has become more complex and have to rely on higher functionality and higher level of compute. Another area of overlap is, as we all well know, and I think that's something that's going to be addressed in the speaking section after me. Cybersecurity and functional safety can help and detract from each other. So the automotive industry has been focusing very heavily on cybersecurity over the last, let's say, decade. As these systems become more interdependent, the vehicles become connected. So there's this general overlap of cybersecurity and functional safety. You can't have a secure system without safety, and you can't have a safe system without security. So you can help. Each of these standards help each other, but can as well detract from each other. And again, this is a very good baseline to ensure that your systems are a good foundation to be able to deploy the functionality in a reliable way. However, as of late, apologies, these systems that enable these active safety and higher features in commercial vehicles, and as well in these more of like robotaxi and transportation as a service efforts, where you're no longer just relying on the driver itself taking care of the vehicle behavior. These systems are becoming ever more complex. The sensors are becoming higher definition. The algorithms are becoming non-deterministic through the rise of AI deployments in the vehicle. And generally speaking, the compute systems are just orders of magnitude more complex and capable. So that means that even if you had a perfectly safe and secure by the letter of the law of today's standards, you still could encounter, without faults in the system, you still could encounter hazardous behavior, because either these systems are encountering scenarios that are beyond its capabilities, and or they're being misused at a very high level. So SOTIF rose from that need. What happens if your system has no faults, but it's still, we need a way in the industry to address risk. So how do you know that the boundary conditions of your system are being properly understood and the capabilities are being properly understood? So the goal of SOTIF, by its acronym, the safety of the intended functionality, is that it allows the industry to at least address the topic. We all take risks, right? Like today, for you guys to arrive here, you took a non-zero risk of getting in a vehicle and driving. There was no 100% assurance that there was no way something couldn't fail and there could be a risk of you driving yourself here. However, you had to make yourself available to come and learn and listen to all of these amazing speakers. So at the end of the day, everybody takes risks at a personal level. Companies take risk, and managing that risk allows you to continue to push the needle in technology and in business, right? So the intent of this enhancement or like continuation of where ISO 26262 left off comes under SOTIF, and the idea is to address the challenge of we don't know what we don't know in these systems, right? So how do you actually articulate that and how you manage that? So an example, in these autonomous driving vehicles, these algorithms may encounter something that you had never trained your algorithms for. How do you handle that, right? Or there's an insufficient robustness in a scenario. Maybe you run into black ice that you couldn't foresee that was there. So how do you handle these different, very challenging environment conditions, scenarios, and degrees of freedom in the autonomous driving behavioral challenges? So let's talk about these hazardous events that could be triggered into your system. So ISO 262 addresses particularly the topics on the left, the pink bubbles. So ISO 262 talks about failures and faults. If your system is having any challenges from either hardware random failure, a latent fault, a transient fault in hardware, a systematic problem, like a software bug, then that could like break your system and you end up in a system failure. That is somewhat understood. The industry has an approach and a methodology and a product lifecycle methodology to address these challenges. But as these systems become ever more complex, then we have other contributors to your system effectively breaking. You may have, in the attempt to deliver higher functionality, your systems may have weaknesses. They may encounter scenarios that, due to the degrees of freedom that the industry is trying to address through these autonomy systems, may have not been encountered before. And then there may be triggering events like misuse or wrong detection of your scenario. So these events could end up like a system failure as well, generating a hazardous event. So how do you handle that? So SOTIF is trying to address this by mapping scenario categories. You have knowns and you have unknowns. You have known scenarios, and then you have unknown scenarios. Unlimited validation and unlimited testing is not economically viable, and you can't foresee every possible scenario being absolutely considered in your algorithm. So you have to prepare in your system definition. So you have to prepare on how to handle this circumstance so you can then address the risk that comes with it. And of course, the risk is that, are you operating safely or are you operating unsafely? So this chart that you see here is precisely what SOTIF is trying to address. All of these in the context of your system may not have any faults at the moment, right? So it's above and beyond what ISO 262 is trying to address, or the cybersecurity standards try to address. This is under no threat, this is under no failure. So it's in the intended functionality, are we being able to stay in area number 1 and number 4? So let's talk about this. So we've mapped 4 areas here of system behavior and scenario class. There's safe and unsafe behavior, and then known and unknown scenarios. So the combination of safe scenarios, whether they're known or unknown, is where you want to operate. So area 1 and 4 is your greens, and then you want to manage the risk in area 2 and 3. So some system behaviors in different conditions that are well understood in the algorithm ecosystem and knowledge base in our industry. You always want to make sure that you are having true positives and true negatives. So what does that mean? It means that you truly understand the scenario and that you are reacting accordingly. So the condition matters, right? Is there truly a critical situation or not? And that you're properly identifying it, right? So in the first line, there's a true positive. So there's an actual critical condition, like something runs in front of your car and you have to apply the brakes, whether it's a level 2 plus ADAS system or if it's an L4 self-driving vehicle, right? This is a critical scenario. The car has to stop. The behavior that properly identifies that critical condition and activates, then yields a true positive. Then a false positive is there's no actual real critical condition, but you misidentify it and you still behave as if it was a positive, and the system activates, and that would be a false positive. So it's not great, it's not a good user experience. Your car may not be driving very nicely, but at least it's not crashing into anything, right? That's kind of like the, we don't say that word, right, in ADAS and AV. Then there's a true negative, when there's no real critical condition, therefore the system does not activate. So you're driving as normal, but this is the other correct behavior of your system. And last but not least, which is the challenge that we want to address, is false negatives. So there's an actual real critical condition, but the system does not identify it properly and therefore has a false negative and doesn't react to it. So this is truly an improper scenario assessment by your system. This kind of situation can be encountered in these unknown unknowns, right? That as these systems continue to evolve and get more complex, we need to be able to address these challenges. Very explicit examples can be very well explained through sensors, through external factors and internal factors. With sensors, it's very objective to identify, and it's a good exercise of thought process of how these external and internal factors could affect your system. So due to the characteristics of these sensors, external climatic scenarios can degrade the capability of these sensors, right? So for example, cameras and radars with rain, light being diffused through the atmosphere in one way or another, snow, are gonna give you distorted inputs. Of course, in your control system, the quality of your input is gonna directly influence your ability to assess the scenario and then activate the proper behavior, right? So as we're building this concept of having a perfectly non-failing system, if your intended functionality does not have the capability because of external factors, you are going to end up possibly encountering unwanted behaviors. In this case, could be either unsafe or just poor experience for your end customers. Another example for radar is interference of other radars or whatever other signals in the environment. So at the end of the day, your degraded sensors could absolutely impact the intended functionality of your system. That's for external factors. For internal factors, there's other topics which could limit the performance or the ability of your system to truly assess the surrounding environment. It could be the resolution, megapixels of your camera, which gives you a reduced distance to assess risk, poor range or limited range. So at the end of the day, you're trying to assess, you can't put infinite sensors, right, that have perfect frequency response in every domain, because that becomes an unpalatable bill of materials for your purchasing counterparts. So what you end up doing is you end up taking a risk and a trade-off in your internal factors, such as the characteristic of your sensors, and this adds up in the ability for your system to address the scenarios and therefore activate behaviors. So the idea here is to lay out the thought process of what are the factors impacting the behavior of my system and how does that amount in risk? And then what can we do to mitigate these risks? So in a nutshell, as the industry has developed these standards to try to ensure that the ecosystem and the supplier base is able to build a reliable and secure mechanism to deploy these solutions into the market, we still continue to encounter that the industry and the technology are moving faster along, maybe from a technology perspective, but in the discipline of being able to deploy and safely offer this technology to the market, the standards are maybe lagging a bit behind. The historical, not super historical, but like the baseline standards that we've been using in the automotive industry as a trend haven't been sufficient to address, philosophically at least, and effectively the life cycle development challenges we have today to be able to adopt this technology. So SOTIF tries to offer measures for risk reduction. This is one of the trends in the functional safety industry, to leverage this sort of approach to address these challenges so that the risk can be assessed and then proper measures can be taken and knowledgeable risk addressing is implemented in the industry. Following our example of cameras, and this is an oversimplification of the system, SOTIF requires an adequate risk reduction of these measures and measures to be taken, right? So for example, in the heavy rain camera topic, then the implication to the behavior of the system would be that you wouldn't drive as fast. Kind of like very clear from a common sense perspective as an engineer, right? But the idea is that this standard is going to help address the requirement of the unknown unknowns, either due to limitation or unknown scenarios that haven't been encountered. In this case, we all understand heavy rain being a known, maybe unsafe scenario for your system to fully behave in, but this is kind of like an oversimplification of the thought process. And then for radar, for example, that if you weren't going to have the proper field of view in your radar sensor, then either increment the capability of your sensors or modify the architecture so that you could get a better sensing technology in support of your near field requirements. So what I wanted to walk you through today in the functional safety domain topic is that historically we had a very clear methodology. We've had to evolve. SOTIF is one of the initiatives in the industry, not the only one, on how to manage these risks that we're all challenged with creating technology to still address the need in the market. Along that, as I was mentioning, we have the functional safety and cybersecurity standards helping us to address this. As well, architecturally, we have to have a way to deliver this to these compute challenges. So the functional safety architectures that are out there, they all have trade-offs. Historically, the automotive industry, following ISO 26262, optimally wanted to deliver the yellow system at the end, a single safety element out of context, like a single component that is able to deliver a safety certification or enable a safety certification, and then you would have a fallback as well as part of your strategy. So that is all great. At some point, the laws of Moore and software architecture and the complexity of our systems come to a point where not every component in your system can have that level of certification. And if you wait, then until the industry is able to deliver everything to a T, then it delays the innovation. So in that trade-off and that fine line of pushing technology and having the industry deliver to like the 100% of the desired optimal requirements, we end up in having to have trade-offs. So in this regard, I have a dial here, and in the gray dial hand talks about the system investment, right? So what, as an industry, we have to address at a system level. And then the component investment, like the tier 1s and tier 2s deliver into the supply chain. So if we wait until all of that component investment is done to a T and all of the technology has been brought to that level of functional safety, the trade-off is that's great at a system investment perspective, because on the furthest right dial, the system investment is as low as possible because the components are carrying that investment. That delivers in a timeline that may not be exactly where the disruptive approach to this technology may be wanting to go. On the far left, we have a decomposition that leverages off-the-shelf components with a concept of leveraging off-the-shelf components that become quality managed, and then doing a decomposition at an application level that rely on software and system decomposition that then leverages ancillary functionally safe components, and that allows you to create a functional safety architecture and rely on these claims as an underlying technology enablement that allows you to make those claims. These components have less investment at that level, and it requires a higher system investment, but at the same time allows for flexibility for leveraging pre-existing technology that may be at the peak of performance. And then a nice in-between is that decomposition with partial component investment and partial architecture decomposition, and it's kind of like a sweet spot of leveraging technology and architectural knowledge. However, how the whole industry as an ecosystem, and particularly in the domain today in the Vector Congress, how the ecosystem comes together and creates those layers of hardware at the bottom, middleware, and application at the top, we all have to be very aware of these decomposition challenges, and that at the end of the day, the intended functionality is being addressed without generating or inserting more risk into the deployment of these technologies. Last but not least, where is this being seen, these architectural trade-off trends in the vehicle? So historically, and this is an oversimplification of the vehicle, Florian earlier had this like massive chart of hundreds of millions of code, right? So nobody's minimizing that. But as we see the major hubs of technology in the vehicle, some have different levels of criticality, and that allows different levels of functional safety architectures being deployed. So if I'm going to populate all of this, clearly automated driving and ADAS applications have a very ancillary requirement for functional safety due to the criticality of their systems. Connectivity, AI, and the kind of like the central server approach to vehicle architectures have needs that can be decomposed in mixed criticality or leveraging off-the-shelf componentry with some ancillary monitoring hardware for functional safety. and continued push of technology into these different fields. That concludes my conversation. So I wanted to bring to you a little bit of what's going on in the industry and the trends, the underlying technology, and where it's not necessarily addressing all of the needs required for us to be able to adopt transportation as a service technology challenges. Thank you.